Hello, everyone. This is Zheng Zhang from Microsoft Research. In this talk, I will introduce PIT, optimization of dynamic sparse deep learning models via permutation invariant transformation. This is a joint work with my colleagues from Microsoft Research. With the evolution of deep learning and large language models, dynamic sparse is more and more prevalent. It exists in both weight tensors and activation tensors, in both input data and model architectures. Also, it exists in both training and inference. For example, dynamic sparse attention is for dynamically attending important tokens to improve attention efficiency, especially for long context scenarios. Multiple mixture of experts dynamically routes tokens to different experts. If we treat the experts as a bunch of weights, only a portion of weights are activated by each token. Very synchronous is an intrinsic characteristic of language processing. For sparse training, training sparse model is very common in model pruning. Even in normal training and inference of large language models, the activation tensors behind some operators, such as ReLU, have high sparsity. However, efficiently supporting dynamic sparse computation is challenging. One reason is that the concrete sparsity of tensors is known only at runtime. Aligning this sparse computation to accelerators on the fly makes this problem even harder. Let's first look at the current compiling technique for dense computation on the left. It splits the computation into tiles. The data are loaded from global memory to shared memory with saturated read-write transaction. The computation of the tile is evenly distributed on the computation cores with minimized bank conflict during data access. So the dense computation is well aligned to each level of the accelerators. However, aligning the dynamically changing sparse tensors introduces a lot of computation waste. One solution is using regular tile to cover non-zero values while skipping the computation of the tiles that have all zero values. If we use small tile, it has low computation waste. But a small tile cannot easily saturate all the computation cores, leading to low SM utilization. If we use large tile, it has high computation waste because each tile contains only a small number of non-zero values. In return, the tile has high SM utilization. We can see from the middle figure that even there is a higher computation waste, 32 times 32 tile performs better than 8 times 8 tile in most sparsity ratios. This implies that SM utilization is more critical than computation waste in modern high parallel accelerators. Another solution is building sparsity-aware kernels. For example, Sparse, Sputnik, Sparta. They build a fine-grained index to skip the computation of zero values. The online data conversion and index construction is very costly. From the right figure, we can see that the conversion overhead takes a large proportion of the execution time, especially when sparsity ratio is high. Because of the conversion overhead, that performs worse than their dense counterpart. So we can see that both regular tile covering and sparsity-aware kernels cannot well deal with dynamic sparsity. In this work, we want to achieve using computation-efficient large tiles with low computation waste and minimal data conversion overhead. The opportunity is online sparse to dense transformation. Let's take matrix multiplication as an example. The non-zero values in the sparse matrices are represented by colored boxes. It is possible to construct dense tile as shown on the right by rearranging the non-zero values from the sparse matrices. For example, along M axis in matrix A. The rearrangement can be out of order. After the rearrangement, the tile A prime and B prime can be multiplied using normal matrix multiplication. The output tile C prime is also dense. When writing it back to C matrix, it follows the reversed order of how matrix A is rearranged. The key of this transformation is that the data rearrangement does not affect the dense computation. So we introduce microtile, the minimal granularity of the data rearrangement. Microtile is a small data unit aligned with the granularity of read-write transaction of accelerators, such as GPU. The read-write transaction in CUDA GPUs is 32 bytes. So microtile is much smaller than traditional tiles. The left are two examples of microtiles. With the online rearrangement of microtiles, the sparse computation can be well aligned to each level of the accelerators, including global memory, shared memory, and computation cores. The right figure shows that once microtiles are loaded into shared memory, the conventional computation-efficient dense tile can be applied. So the three levels are all aligned even for sparse computation. We introduce two primitives, sRead and sWrite, to do the online rearrangement of microtiles. The rearrangement is piggybacked during data movement from global memory to shared memory and also in the opposite direction. Due to the aligned data granularity, the access to sparse data can be purely random without any cost. With sRead and sWrite, we can come up with a very simple and clean sparse kernel template, as shown on the right. It first allocates the shared memory for the tiles of input and output tensors. Then, sRead loads the non-zero microtiles from the sparse matrix to shared memory, following the online constructed index of the microtiles. After the data in shared memory is ready, a normal dense tile computation is executed. Then sWrite writes the output from shared memory to its corresponding locations in global memory. This template makes existing high-efficient implementations of dense tiles easily plugged in. As Pete assumes that data rearrangement does not affect the dense computation logic, we call this kind of data rearrangement permutation invariant transformation. Permutation invariant transformation is the data permutation along an axis of an operator. If any shuffling of the data along this axis does not affect the correctness of the operator, this is permutation invariant transformation. This axis is called Pete axis. More precisely, the computations on Pete axis satisfy the commutative and associative. We find that Pete axis commonly exists in deep learning operators. As shown in this table, most axes are Pete axis. For the convolutional operator, axes x, y, I, j are not Pete axis because there is arithmetic operations on them. That is x plus I and y plus j. Further, we introduce the concept Pete rule. It represents a concrete permutation invariant transformation of an operator. It is composed of a Pete axis, a concrete microtile shape, and a specific dense computation tile. Given our operator, a bunch of Pete rules can be derived with the combination of different Pete axes and different dense tiles. For constructing the best sparse kernel for online execution, we use the statistical method, that is using some sparse tensor samples to evaluate the performance of the derived kernels and select the best one. This is how the sparse kernels are derived. An operator usually has multiple Pete axes. It also has different dense tiles with different shapes, such as 32 times 32, 64 times 64, which are stored in a tile DB. The combination of a PIT axis and a dense tile produces a concrete sparse kernel. The compiled sparse kernel should be coupled with online sparsity detection and index construction. The detection and construction have very low overhead thanks to microtile and permutation invariant transformation. PIT only constructs index without reformatting the sparse tensor, unlike the sparse tensor formats such as CSR, which build their index with reformatted data. The index construction can be fully parallelized in an out-of-order manner thanks to permutation invariant transformation. It detects non-zero values at the granularity of microtiles. This figure illustrates the online execution. After the index is constructed from the sparse tensor, both the index and the sparse tensor are fed to sRead for loading to shared memory. Let's recap PIT design with its overall workflow on dealing with dynamic sparse computation. It's a JIT compiling process. It uses several sample tensors to select the best efficient microtile. Based on the selected microtile, it compiles the sparse kernel following the sparse kernel template. During online execution, PIT detects the sparse tensors, constructs indices for them, and feeds them to the generated sparse kernels. We comprehensively evaluated PIT using 6 popular transformer models with different data sets, different precisions, and accelerators. PIT works both for training and inference. We compared PIT with 6 end-to-end inference libraries and 4 sparse kernel libraries. The baseline PyTorch-S is a variant of PyTorch that uses the best performing sparse kernels from the following sparse kernel libraries. Due to time limit, I will only show some representative workloads. You can refer to our paper for more evaluation results. The first one is end-to-end inference of OPT, which is the large language model that most like GPT. We evaluated it on 8 V100 GPUs. They are more than 2 times speed up compared to the baselines. The performance gain comes from varying sequence length and activation sparsity. For varying sequence length, PIT can only compute the effective tokens without computing the padded tokens by dynamically covering the effective tokens with microtile. For activation sparsity, the activation tensors after ReLU operator in OPT have more than 90% sparsity. PIT uses a proper microtile size to cover the non-zero values in those activation tensors, only do the effective computation. It brings additional 27% speed up. The right figure shows that all the solutions have similar memory usage. The second one is end-to-end inference of switch transformer, which is the first MOE model. We evaluated it on an A100 GPU. PIT is 1.6 to 7.8 times faster than the baselines. The performance gain comes from PIT's efficient support of MOE and the varying sequence length. In this experiment, multiple experts are on one GPU. The matrix multiplication of each token with its corresponding expert is usually larger than a microtile. So the microtile can dynamically cover all the computations of MOE without introducing any computation waste. Also, in PIT, there's no need to rewrite the input tokens of MOE, in contrast to the baselines, which reorganize the input tokens for each expert. So we can see that the optimization of MOE contributes a lot to the performance gain. For PyTorch-S, it has to convert sparse tensors into sparse format. The conversion overhead contributes a lot to the execution time. The right figure shows that the memory usage of PIT is low. Here, DeepSpeed's memory usage is high due to implementation issue. Their new version has similar memory usage to others. We also evaluated end-to-end training of OPT on an A100 GPU to show that PIT also works well for training. PIT is around 2 times faster than the baselines. The performance gain comes from varying sequence length and sparse attention. Here, varying sequence length is a major source of the performance gain. For the lower triangle attention in OPT, microtile makes computation waste smaller than the traditional block sparse. PyTorch-S is faster than the other 2 baselines because it uses sparse attention from Triton. The right figure shows that the memory usage of PIT is low. At last, we show one micro benchmark to demonstrate conversion overhead of sparse index. We did this experiment on a V100 32 gigabyte GPU. It is generating sparse index for 496 times 496 sparse matrix with 3 different granularities, sparsity granularities. For granularity 1 times 1, PyTorch-S uses cuSparse. For the granularity 16 times 16 and 32 times 32, PyTorch-S chooses Triton. We can see that PIT is much faster than PyTorch-S. The performance gain mainly comes from out-of-order index construction and a zero copy of data. So PIT makes online index construction much more practical than before. To conclude, PIT demonstrates a novel and effective way of handling dynamic sparsity, which is a growing trend in deep learning models, especially for large language models. For example, MOE, dynamic shape, continuous batching in LLM inference. With permutation invariant transformation, PIT achieves high computation efficiency, low computation waste, and minimal data conversion overhead. Furthermore, the idea of decoupling data format and computation logic in PIT can be generalized to other compiling scenarios, such as low-bit computation, mixed precision. Yeah, this is all my talk. Thanks for listening.
Okay, this is your chance to ask questions. Please come up to the mic and give your name and affiliation.
Hi, this is Xiaoniu from Shanghai Jiao Tong University. Can your system automatically discover sparsity in applications, even in dense operations?
Yeah, thanks for your question. Yeah, our system can automatically detect. Let's look at this slide. In order to compute the effective computations of sparse tensors, our system has to first discover the non-zero values in the computation on the fly in an online manner. Yeah. So the system built the corresponding GPU kernels to detect the non-zero values, and the detection is in the granularity of microtile. Yeah. The detailed approach is that we use different thread block to discover the non-zero values of different regions of the sparse tensor to build the index of the non-zero microtiles.
Okay, thank you very much.
Okay, we have another question here. Yep.
Zheng from Amazon. So if I understand correctly, so during the computation there is a write and a read overhead, so which introduce like a memory copy. And in your presentation, it seems there's only limited memory overhead. So I'm thinking, is that because the matrix is very sparse, like 90% of it is 0, then you do not have many memory copy. So that's the reason, or you have other explanations towards that function, that direction?
Yeah, thanks for the question. Yeah, we don't. Our system don't have to rewrite the sparse data. For example, for the traditional sparse format such as CSR, if we want to transform the dense tensor, the dense tensor has a lot of zeros. into the sparse format, it has to rewrite the non-zero values in this tensor into copy these non-zero values into the CSR sparse format, right? And in our solution, we just build the index. The non-zero values like this. The non-zero values in the sparse matrix is still there. We don't copy them. We just build the index to index the non-zero microtiles. So there's no additional data copy cost compared to other sparsity solutions.
I see. Thanks.
Okay, if we thank the speaker once again. Thank you very much.
Thank you.